also like to pay respects to the elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who are present here today. Today we are going to have a presentation by Eve Slavich. She's one of our consultants, and she's going to talk to us about multiple comparisons. For those of you who are joining us for the very first time, we are Stat Central. We're an organization within the Mark Wainwright Analytical Center and the Division of Research, and we provide statistical consulting services for people at the university. So HDR students and research faculty across all faculties in the university can come to us for some research design advice and advice on the analysis of their data. And one of the things that we do is present monthly seminars that are free and open to anyone to attend that address very common basic statistical and research design issues that we often see in our consulting practice. And one of the things that we are often asked is, how do I deal with that multiple comparisons problem? Or what even is it, and why do I have to even think about it? This is such a common thing that this is the second time we've had a presentation on this. So because it is always something that researchers are having to deal with, and they're not quite sure what to do. So Eve's going to tell us a little bit about what multiple comparisons are and give us some guidance on and suggestions on what to do. So go ahead, Eve. Thank you very much.
So how's my slides? Visible?
Good.
It's good. Yep. Why does it say screen sharing is paused? Is that working? Resume share.
I can see it.
Okay. Yeah. Okay. Yeah. So yeah. So I just thought this is a classic XKCD comic, which just illustrates the problem of multiple comparisons. That I think there is a lot of people know what these are, but just in case you don't, here's some people, jelly beans cause acne, let's investigate. They don't find a link between jelly beans and acne. So then they hear that it's only a certain color that causes it. So they test 20 different colors and they're not finding any associations at the 5% type 1 error rate. Oh, but we found a link between green jelly beans and acne. Whoa. And the news is that green jelly beans are linked to acne. And there's only a 5% chance that that was a coincidence. I'm just going to skip straight to this. So what they did here was conduct 20 statistical tests. And every time you conduct a statistical test, you have a chance of making a type 1 error. So when you do 20 tests, you have 20 chances of making a type 1 error. So that is where you reject the null hypothesis, but the null hypothesis was actually true. So it's a false positive discovery. It's usually where you say that there's an effect, but there was actually no effect in the population. And usually, the alpha level that you set, that's the level of type 1 errors that you're willing to accept. So when you say I'm going to reject the null hypothesis, if it's the p-value is less than 0.05, you're saying you're willing to accept a type 1 error rate of 5%. So multiple comparisons where you do multiple statistical tests are really, really common. You might have multiple treatment arms and you have all these planned comparisons that you wish to test. You might have multiple outcome variables. So this is how the chance of making a type 1 error goes up with the number of hypotheses tested. You can describe the probability of making a type 1 error with this equation here, 1 minus alpha to the m, because each time you conduct a test, you have 1 minus alpha to the m, a 1 minus alpha chance of not making a type 1 error. And then, so you then multiply, you raise that to the power of m for each test that you do, where m is the number of tests that you do. So yeah, as you can see, like by the time you're doing 25, 50 comparisons, you're almost certainly going to be making a type 1 error, and that's not good. And even with only a few tests, like less than 10, you still have a much higher rate of making a type 1 error than 5%. There's kind of two approaches to this. There's these two things called the family-wise error rate and the false discovery rate. So the family-wise error rate is the chance of a false positive in at least one hypothesis test. So one thing that people try and do is control the family-wise error rate. So they say, I'm going to do 10 tests, and I only want a 5% chance of a false positive in any of these tests. The false discovery, and so if you use Bonferroni or Holm, Bonferroni-Holm or Tukey, you are controlling the family-wise error rate. An alternative that can be handy in some contexts is the false discovery rate. So the false discovery rate is the proportion of discoveries. So these are rejected null hypotheses that are false, so incorrect rejections. So that's where you're making a type 1 error. So for example, if you control the false discovery rate, I think that's on my next slide actually. So let's go here. So the family-wise error rate is the chance that one of these red null hypotheses is wrong. So let's say the red null hypotheses are p-values that are less than 0.05, for example, and the blue ones are where we had high p-values. If we control the family-wise error rate, we want a 5% chance that one or more of the red conclusions is wrong, no more than 5%, let's say. If we control the false discovery rate, we say that amongst the red conclusions, 5% maximum are false discoveries, so false positives. To sort of compare these two, the false discovery rate is more sensitive. So it will generally mean that you'll get more of your hypotheses in your set of significant hypotheses. And this can mean that you have greater statistical power. So the power to detect an effect that is truly there. But you can't be sure of any particular hypothesis test. You know that some will be false positives, but you won't know which ones. If you control the family-wise error rate, it kind of means you're sure of every single test result at the 5% level. So you're sure that, or whichever level you choose. So if you don't want to miss anything, and the cost of a false negative is high, then it might make sense to control the false discovery rate. But if you want to be sure of every single hypothesis, you don't want to make type 1 errors, then you want to control the family-wise error rate. So here's another thing about them. If you control the family-wise error rate, the more tests that you do, the less power you get. So you're losing power to detect your true positives. If you control the false discovery rate, you lose power as you add more tests, but only if they're tests with no true effect. And I'm going to illustrate this with some examples. So this is the strategy I'm going to illustrate for controlling the family-wise error rate, the Holm-Bonferroni adjustment. And there are other tweaks to this, but they're all sort of variations on the theme. So Holm-Bonferroni is good because it's quite general. If you've got any family of hypotheses that you want to control the family-wise error rate across that family of hypotheses, what you can do is rank the p-values from smallest to largest, and then step through, starting with the smallest p-value, compare them to alpha over m minus I plus 1. So what does this mean? So if m is the number of hypotheses and I is the I hypothesis that you're doing. So if you were comparing, if you were doing 5 hypotheses, a family of 5 hypotheses, so m is 5, and you wanted the family-wise error rate to be controlled at 5%, your first p-value, you would compare it to 0.05 divided by 5. So you would reject your first hypothesis if it was less than 0.01. So yeah, 0.01. Yeah, that's right. So and so forth. And so you can see, like, your smallest p-value has to be a fair bit smaller than 0.05 to be rejected. And the first non-significant hypothesis, like non-rejected hypothesis, you stop testing, and all subsequent bigger p-values are considered not significant. And there's a conversion that you can do to convert the p-value to the adjusted p-value, which means all you have to do is compare them to your alpha level. Yeah, this is preferred to the Bonferroni adjustment, which is known to be conservative. So it has less power to detect a true positive. I didn't tell you what Bonferroni was. Bonferroni is just where you divide alpha by the number of tests. So in the jelly bean example, you're doing 20 tests. So you reject the p-value if it's less than 0.05 divided by 20, for example. And you just have a flat rejection threshold. So how do you do this? I'm demonstrating in R, but all statistical software have ways to do it. And you can also do it. The first way I'm demonstrating how to do it, like in a calculator way. You can do it by hand, basically, or even in Excel. So Julia is comparing the effects of 4 treatments to a control on blood pressure. So she's decided that she's going to do 4 planned comparisons. She's going to compare treatment 1 to the control, treatment 2 to the control, treatment 3 to the control, and treatment 4 to the control. And she gets these p-values. They're all unadjusted. And so she can just take m to be 4, and she can calculate the adjusted p-values by timesing them by this, m minus rank of the p-value plus 1, and that converts these to adjusted p-values. And if you do that, then you can just reject at the 0.05 level. And so she finds that the first hypothesis that is that treatment 1, she rejects that it's the same as control. And all the others, she finds that there's no evidence that they're different to the control. And you can use this built-in R function to just take that vector of p-values and adjust them with the Holm method, so p.adjust. So if you don't want to concentrate on the code, that's fine. What I'd like you to concentrate on is the concepts, but I'm including the code so you can see how to do it. If she adds in 2 more hypotheses, so she's going to do 6 comparisons, but on the same data set, and these ones, so comparing additional treatments within, comparing like treatment 1 to treatment 2, for example. And say the p-values that come out from these comparisons are 0.02 and 0.01. If she adjusts the p-values now, the interesting thing is that now at the family-wise error rate of 5%, she can't reject any of the hypotheses. So the principle that I'm illustrating here is that the more tests you do, the less power you get. So without collecting, one way that she could get more power is to collect more data. And another way on the same data set is to be selective about how many hypotheses she's going to test a priori. And I guess if you're doing a power analysis, you probably need to take into account if you're going to have to adjust your p-values. So now the Benjamini, so that's the family-wise error rate. And yeah, the main principle is like, if you're adding in tests, you're going to lose power. The Benjamini-Hochberg adjustment controls the false discovery rate. So you do a similar thing. You rank the p-values from smallest to largest. And then you also start with the smallest p-value and you compare it to I over m times alpha. So if you were doing 5 tests, the first p-value you would compare it to, and let's say you're wanting a false discovery rate of 5%. The first p-value you compare it to 0.01. The second p-value you compare it to 0.02. The third at 0.03, and so on. And the first time you reject a hypothesis, you stop testing, and all your subsequent hypotheses are not significant. And you can also convert the p-values to an adjusted p-value, which means you can just compare them to whatever the false discovery level that you want is. So the standard false discovery rate varies a bit, but people do use higher false discovery rates than family-wise error rates. And it's usually when they're conducting an extremely large number of tests, and they don't want to miss out on true positives, and they don't mind if they're making some false discoveries. So, for example, in genomics, there might be thousands of genes, and you test them all, and you get a set of like 80 genes that might be important for some condition, and you know that 10% or 20% of these 80 may be false discoveries, but you don't mind because that's going to lead you into like your subsequent studies. In R, it's very easy to adjust the p-values using Benjamini-Hochberg, using the same function, p.adjust and method equals FDR. So let's have a look at an example of what happens in practice. So again, don't worry too much about the code because I'm going to talk through it. Lena is testing for an effect of any of 110 genes on a health outcome. So she tries to control the false discovery rate at 5% and 10%. And so let's say out of the 110 genes, 10 of these genes affect the outcome, but 100 don't, because I'm simulating p-values. So I'll simulate 10 genes which have an association with the outcome, and 100 I'll simulate randomly. So we would expect 5% of these 100 genes will be false by chance, assuming a threshold of 5%. So she calculates her 110 p-values, and she finds that 15 are less than 0.05. She doesn't actually know that she's got 10 genes. This is just from the simulation. So if she uses a false discovery rate of 5%, she doesn't reject any hypotheses. But if she uses a false discovery rate of 10%, she rejects 12 hypotheses. So this is what she did here. Her raw discovery rate is 15. That's her raw discovery count. And her discovery count at the 5% level is 0, and her discovery count at the 10% level is 12. And I assumed that for her true positives, she got evidence always less than 0.01 from her sample. So I just want to show you what happens if we add more genes where there's no effect. So she decides to test 210, but she still only has the 10 important ones, and she's just added in another 100 ones that aren't related. So she now calculates 210 p-values, and she gets 18 that are less than 0.05. So this will include her 10 true ones and 8 false ones. So if she calculates her discovery count at the 5% level and at the 10% level, she's now getting 0 that are considered significant. So so she gets terrible power. She's not detecting any of the true positives. But if she upped her false discovery rate, she might detect more true positives as well as false positives. However, the situation is better when she has more evidence for the true positives. So let's say that she tests the same 200 hypotheses, but now she collects more data. So now her true positives, because they're truly there, we expect that the p-value will go down as you collect more data. And she gets p-values less than 0.001 for these true positives. but the false positives, that those p-values could be anything. So if she tests these 200 hypotheses and controls the false discovery rate at 5%, she gets 10 null hypotheses that she can reject. And if she controls the false discovery rate at 10%, she gets 11 null hypotheses that she can reject. So this is pretty good power now. She's finding all of her true positives and she's not making too many false discoveries. So I guess my take-home message is that the more hypotheses that you want to test, the more evidence that you're going to need to claim that some of them are significant. And I just wanted to say that if she now add, if more of her tests, if you're controlling the false discovery rate, but you add in more true positives, that does not affect your power when you under Benjamini-Hochberg. So now she tests 140 genes and 40 of them affect the outcome. So rather than adding in kind of nuisance tests, she's adding in tests where she's finding the effect is where the effect is really there in the population. And so I'm just saying she had enough data to get p-values less than 0.01. And her raw discovery count was 43. So she had 43 p-values less than 0.05. And when she controlled the false discovery rate at 5% and 10%, she rejected 42 hypotheses. So again, we didn't catch too many false positives and we caught all the true positives. So with the false discovery rate, it's not that bad to add in tests where you think there's going to be an association, but it's particularly bad to add in tests where there's unlikely to be an association. And this is just to compare the false discovery rate to the family-wise error rate. So now I'm saying she's testing 500 hypotheses and 400 affect the outcome truly. So similar to before, 403 get p-values less than 0.05, and the false discovery rate, controlling the false discovery rate means that she rejects all 403 of these p-values. So she's making 3 false discoveries and finding her 400 true positives. But if she controlled the family-wise error rate at the 5% level, she would find an association between 3 genes and the outcome. So we definitely do lose power if we choose to control the family-wise error rate, even if there's a lot of true positives. So controlling the family-wise error rate, we can only be sure that 3 of these hypotheses should be rejected. But we know that 400 of them were truly false. So both of the methods lose power if you add a lot of noise or nonsense comparisons. P-values can generally be reduced by increasing your sample size, and that will give you more power, like including if you're making multiple comparisons. And there's tweaks to the adjustment procedures to get slightly higher power, but there's no silver bullets. So yeah, I'm not going to go into all the tweaks, but there is a lot of literature on improving the Benjamini-Hochberg procedure or the to get more power, but it doesn't get around the main problems of adding too many nonsense comparisons. So I guess both of those strategies don't take into account any correlation that you might have between your hypotheses. So sometimes when you have correlated outcome variables, you might be able to borrow strength across variables. And this actually applies for correlated hypotheses. So for example, if Sam was measuring all these physiological variables like activity, heart rate, respiration, blood pressure, and weight, and he's trying to determine the effect of a treatment on these variables, these are his outcome variables. We'd expect that if the treatment affects one, it might affect another, and so those tests will be correlated in their in what their effect size is. And this is a sort of a similar setup. Arjun measures a host of biodiversity indicator variables, like these might be species richness, species diversity, to determine the effect of a bush regeneration project. So he thinks these variables might be correlated and they might respond in similar ways to bush regeneration. There's slightly fancier things that you can do in these situations that require a bit more coding. But you can take a simulation approach to control the family-wise error rate. And you can also do this for the false discovery rate by simulating correlated outcome data from the model, like under the family-wide hypothesis of no treatment effect. And then, so you simulate data with no treatment effect across any of the variables. And then you test your M hypotheses on the simulated data. And you commute the treatment labels and test the hypotheses again. And then you basically want to figure out what threshold, like you might start with 0.001, corresponds to your desired type 1 error rate, a family-wise type 1 error rate. So for each threshold, you count up the proportion of the simulations in which at least one test was significant, and then and you work out where which threshold is equal to delivering a type 1 error rate across the family of hypotheses of 5%. So yeah, it's a bit of effort and custom coding, but it can get you more power when your hypotheses are correlated. And the last strategy for multiple comparisons is just not to do them, not to do so many tests. So sometimes you can develop an index which combines variables. So these are when your multiple comparisons are due to multiple outcome variables, but you might be able to develop an index that means you can just do one hypothesis test instead of a bunch. So combining all the biodiversity ones into something like the inverse covariance weighted mean index. And you may also be able to take a multivariate approach. So you look for a treatment effect on the multiple outcome variables simultaneously. And so I guess this approach is the trying not to make too many, perform too many hypotheses when you're kind of interested in like a treatment effect on a group of things all at once. And yeah, this is really the end, but I know that there are other things out there. There's Tukey's test and Dunnett's test, and these are good. Like, these are good. I didn't talk about them much, but they're, if you're doing multiple comparisons for the specific scenario that they apply to, they're the best thing. So Tukey's test is when you're doing all pairwise comparisons between the levels of a factor. And Dunnett's test is when you're doing like a many-to-one comparison, like comparing treatments A, B, and C to a control. But you can't use it in any other situation. And they're available in all decent statistical software. And this is my conclusion slide, but I think I might just leave it sitting up there and take questions.
Thank you, Eve. If you guys have any questions, you can put them in the chat, or you, if there aren't too many, you can just mute yourself and ask a question, or you can put your hand up and we'll see it in the participants list and say, hey, what do you have to say? Okay, Eve, there's a question in the chat. This is from Tim. I have a question about the situations you mentioned in which there are local correlations within your data. For example, there's spatial correlations, such as with remote sensing, fMRIs, hotspot detection, etc. Do you know of any purely analytical way to estimate the family-wise error rate or false discovery rate in this case? For example, incorporating the coordinates themselves into your model, or is random permutation really the only way to estimate the null distribution?
I'm not sure what the hypotheses are that you're testing. So I understand that you've got correlated data. The correlation that I was talking about was correlation between the hypotheses that you're testing. But it's true that H0, hotspot X is significantly different to the rest of the domain. And then you might be testing and that, and then you might be doing that for a bunch of H0s. I'm sure that you could dream up a simulation-based approach there. It's probably beyond the scope of my ability to answer here. Probably have to spend some time in a consultation with you for that one. Not sure. But that's an interesting question. Yeah, when you've got, because the correlation between the hypotheses is going to be spatial, but I think you'd come up with the same, you need to be able to simulate model, data under your null distribution. Yeah, I'm not sure. That's a complicated one. Thanks, Tim, for the question.
There's another question. Is it a good strategy to use family-wise error rate for low H's, I guess the number of hypotheses under 10, for example, and use false discovery rate of more than 10?
It's not really, I think in practice, when people are doing a lot, that ultimately what they go for is, if they're doing a lot of tests, they control the false discovery rate. If fewer tests control the family-wise error rate, but really I think it should be driven by what's important to you. So if you really don't want to miss your true positives, and then you go for the false discovery rate. But if you want to be able to claim that every single claim that you're making, you've got good evidence for it, then you want to control the family-wise error rate. So it kind of depends on where you're coming from with your research question. And if you don't control the family-wise error rate, you know, your research is definitely open to, you know, drawing spurious conclusions. And if that's quite controversial in your field, then that won't go down well. So yeah, so I think that's where it comes from. Yeah, no one's asked like, what's your family of hypotheses? Kind of avoided talking about that in the talk, but yeah.
Hey Eve, what do you define as a family?
Yeah, because that's something that's also not very, there's not really an answer to that. So yeah, I would say it's yeah. Should have.
It's a hard
made
question.
a slide on it, yeah. But basically, you know, I would say that always, if you've got a single model with on a one data set, one response variable and multiple predictors that are generating your multiple hypotheses, I think that's always one family of hypotheses for me. But you know, just because it's on independent data sets doesn't mean it's not the same family. But yeah, you know, you could control the 5% family-wise error rate across your whole paper, which might use more than one data set, or you could control it data set by data set. But even controlling it data set by data set, it means that if you collected 20 data sets, or maybe you've looked at 20 data sets from different sources, if you only control the type 1 error rate at 5% within each data set, then you're expecting to make type 1 error above 5% across all of those. So yeah, there's different conventions in different fields. I think it's more like, just think about what will pass the pub test, the science pub test, and go with that.
Is there anything wrong with cherry picking the comparisons you choose to look at?
Yeah. So I guess this is all assuming that, like with all hypothesis testing, you should really define the hypotheses you're going to test before you collect the data, and before you inspect and plot and look at the data. They don't, all of these hypothesis tests don't condition on the fact that you might have done different like inspections of the data, and also if you drop out comparisons, as you can see, it will affect how many become, like it will affect your family-wise error rate. So you can see some meaningless comparisons and drop them out, and then adjust your p-values without those ones in there and get more significant ones. But that's kind of not very like that's going to lead to a false family-wise error rate. So even though you say you're controlling your family-wise error rate at 5%, it's likely that you'll have a higher one. I hope the statisticians agree with that answer. Yeah. I don't know what
Oh, I see. I see.
Okay.
Yeah.
Yeah,
There's,
okay, yeah, that
yep.
that I see what
Yep.
you're saying.
Yep.
Yeah, that's fine. Like if you use a software that does some comparisons that you're not wanting, then yeah, you cannot, you don't have to use them.
Yeah, I just did this with the EM means where I had a bunch of pairwise comparisons that could be done. But so I did them all, but not doing any adjusting, and then took out those pre-specified pairwise comparisons from the results. So going from 12 different comparisons down to 4, and that's what I adjusted.
Yeah. Cool.
Okay. If there aren't any other questions, thank you very much, Eve, and thank you everyone for coming, and look out for our announcement for our October seminar, which will probably be about October 21st or so. And have a good day. Thank you.